The first speaker of today's workshop is Professor Maya Simon from the University of Network. So he will talk about the local geometry of Ricci flow. So that's Professor Maya.
Yeah, thanks very much to the organizers for the invitation. It's great to be in Taiwan again. This is my second time here. First time was in Hsinchu, and now we're in Taiwan. I'm really enjoying the conference, so thanks again for this invitation. Yeah, so today I'll be talking about some local geometrical aspects of Ricci flow. So let's have a look at the situation. So we're interested in a smooth manifold, so I'll denote the dimension always with a little indice above there, dimension n. So my m's are always going to have no boundaries, but they could be open. Okay, so I'm not assuming these things are necessarily closed or you know, of any other type. We're allowing things that are open. And remember, we say that something is a solution to the Ricci flow if this whole thing, g of t, is smooth in space and time on m, and we have the Ricci flow equation, which we've seen many times in this conference in various different forms. But remember, just for the moment, we want to allow all sorts of Ricci flows at this point. So here, all we're saying is m is smooth. So I'm not looking at necessarily a closed manifold here or a non-compact complete space. Nothing about completeness here. So just keep in mind at the moment that we're really going to consider the possibility that this thing is just a part of a manifold or something like that. Okay? This will come up a number of times. Okay, so here I'm always looking at intervals for the solution, and we can introduce my notation here. So Ricci, RC is the Ricci curvature, G is the metric, and if you see a little r, my r will always refer to the scalar curvature. Okay, so the r is going to refer to the scalar curvature, and I'll make a distinction between the Riemannian curvature and the scalar curvature by writing a little rm. So this is the full Riemannian curvature tensor. This is, of course, a 0,4 tensor. This is a function, and this is a 0,2 tensor, just like the Riemannian metric. Okay, so that's the notation and the setup. Okay, so we've seen this result also a number of times. So just remind us of it, because we'd like to use this a number of times. So if we have a smooth manifold, and I'm introducing some notation here, and it's complete. So I'm always going to put a little red CMPL for something which is complete, and BC if I'm talking about it's got bounded curvature. So we take one of these manifolds which is complete and has bounded curvature. Bounded curvature means the supremum of the curvature is less than infinity. Then we know there's a solution from Hamilton and Xi to the Ricci flow for a short time, depending on this K0. And in fact, Bing Long Chen and Peng CP2 showed that this thing is unique. So you can actually see that the solution is unique. And what do you mean by unique? In the class of solutions where the supremum, say, of the curvature is less than infinity on this whole m times this time interval here. So that's what I mean when I say it's unique. So the uniqueness is not actually important for this part of the talk. The usefulness of the uniqueness is that we can talk about the Hamilton-Xi solution. Okay, there's not a lot of them, there's just one, right? Okay, and this solution is, of course, complete and has bounded curvature. Okay, like I said, in the theorems and discussions that I'm going to go through in the next talk, and also in the talk in the following, we really want to consider the situation that maybe the solution you have is not complete. Maybe it's not compact, and maybe it doesn't have bounded curvature for some t or all of t. So we've got this nice setup. If you start off with something with bounded curvature, which is complete, then you get a unique solution with these properties. But of course, there are other situations where this is not necessarily going to be the case, right? But we still want to understand things about such solutions. In particular, we're interested in sort of estimates and local properties of such solutions. Okay, so that's what this talk is really about. It's about local results for the Ricci flow. And just before we get into the situation that we may be going to remove these things, let's just remind ourselves once again of what's known about the local behavior of the Ricci flow. So, wow, this is the theorem that shows us the Ricci flow has this nice local properties, that it really has these local features which are a little bit unusual, are not the case for linear flows. So let's just remind ourselves of the theorem of Perelman. We see that there's a sort of local behavior of the solution. So if you take any dimension and you take any small alpha, then you always find a small delta such that if you know your initial ball of radius 1, say, is almost Euclidean, what are the conditions? That is, the scalar curvature is, say, bigger than or equal to -1 on this ball, and you've got almost the isoperimetric inequality from Euclidean space. So here, if I didn't have this little delta here, and I just have bigger than or equal to Cn, where Cn's the one coming from Rn, then we would be, in the case of Rn, the inequality. But here we're showing we've almost got it for all domains in there. Then this is the first, I call this the first pseudo-locality theorem of Perelman, because there are, of course, 2 in the paper. But this is the one I'll be more interested in this talk here. Then you get that things smooth out on a small region contained in your initial ball for later times, right? So this is when we see this, we see immediately, okay, so this Ricci flow has this sort of localizing property, okay, so that if I know something about my ball at time 0, then I can say something for a short time for a smaller ball at later times. Now you notice I'm putting this CMPL and BC in here because the proof of this pseudo-locality theorem uses these features, CMPL and BC, the proof given by Perelman. And this is an important, these are needed for the proofs, at least the existing proofs of Perelman's result. So we just want to make that clear at the moment. This is the class of solutions that are considered to get this localization. Now, I said at the beginning of the talk, we don't necessarily want to consider these things. So we're interested in maybe can we remove them? That's one minor issue, or I shouldn't say minor, it's one issue. We're also interested in just getting different sorts of local estimates. Okay, and as I said, this Perelman's pseudo-locality theorem, the interesting thing about it is that this sort of behavior is local, and it's not going to happen in the linear case. So let's just stress this one point I'm making at the moment. This is an almost local result, right? So your knowledge on this ball at time 0 tells you knowledge about the ball at later times of a smaller radius, where these times and this smaller radius depend on the information you have at time 0. And the point I was making about almost, at least in the proofs we have, really this statement here should be knowledge of the ball at time 0 and knowledge on the class of solutions. So somehow in the proof we're assume something about the solutions. So that's a little bit dissatisfying, right? We want a purely local result, which tells us just take any Ricci flow you know something about maybe time 0 and hopefully very limited information about the solution, maybe nothing. We would like to get a sort of local result. Okay, so the picture of this sort of result is, I think, well known. So the idea is you've got this sort of, you don't know what's happening here, but then you might have a nice area here. Here's my x0, here's my radius of 1. This is my manifold at time 0, so you've got this nice, it might be a really shallow cone, so there could be an incredible amount of curvature here. Maybe it's just a shallow cone, but it's just smoothed out there at time 0. And then under the Ricci flow, what this thing is saying is that this is getting nicely smoothed out if I go in a little bit, so now it's getting even better. So a little later here, you've got almost a cone-type singularity, and then later on a smaller ball here, right, so here's the distance delta now. who knows what's going on in this part, could have lots of topology and so on, but we're getting control in this region here. Okay, at least for times depending, at least for a small amount of times depending on alpha and the initial, let's see, what did I call it, t, and how close you are to the Euclidean situation. Okay. Right, so that's just the reminder of the setup and also some points I wanted to make about the situation here. And just also the other interesting fact is that this sort of behavior doesn't happen at all in the linear case. So if we have a solution to heat flow, for example, so you start off with something which is really high up. So this is a graph of some function at time 0 going from R to R, and we're looking along here. This is my, say, x is equal minus 1, x equal to 1, and this is 0. So we've got a region maybe where the initial graph is 0, but this is a very large number here, say n. So if you go a little bit further out, it's way up. Then we know under the heat flow, this thing shoots up incredibly fast depending on how big n is. It's going to stay below n, between n and 0, but it's going up really quickly. So it's going up at an incredible speed here. And in fact, you can, if you arrange things quickly, so what we see is there's no, even though this is 0 here, it's not, if we go in a bit further, we can't say it's close to 0 or anything. It's going to shoot up as fast as you like, actually. You can show that at this point here, by choosing n big enough, you can actually get any power, for example, of, you can get any power that you like. Sorry, that's the wrong sign there. Big and equal to 1 here. For any at this, so you can find, I'll take this x0 is in the middle. Here my x0 is equal to 0 here. And you can always arrange things by choosing n large enough that this is the case for some t as very small. So actually you can get it as small as you like. So essentially you see that this behavior is not happening at all in the heat flow situation. Okay, this thing shoots up at incredible speed. So here, this, it was 0 in a nice region. It's identically 0. Knowledge of this region doesn't give you real knowledge later on. It's not enough. So it's the nonlinear behavior of the Ricci flow which is causing this interesting behavior here. This is in the heat flow here, I'm just talking about any time. It's just a short time information for the heat flow. You're talking about the Ricci flow now? Well, this T you get depends on the information you have. I mean, you're not going up to any singular time at the moment. You're staying in a region, well, you don't know what's happening outside, but in the region you're looking at, it could be there's a singularity occurring outside. So you can only get this estimate as long as the solution exists, of course. So this, when I say T, depending on the information that you have and, of course, the existence time, as long as the solution is existing. Maybe there's a singularity happening outside. Yes, this is possible. Yeah, sure. In fact, this will happen quite often. Yeah. Okay, so, right. What we're interested in doing is, like I said, getting some other local results and sort of trying to maybe weaken some of these conditions here. So, right, I've said that for the heat flow. Now, somehow this completeness, you notice I had this CMPL here. This is going to be important because you're going to need some sort of local completeness condition. Why is that the case? Well, there's this example of Peter Topping. In fact, we've seen this sort of picture I'm drawing here in an earlier talk. Draw it like this. So if you take this very long cylinder with a little cap on the end, so it's got an incredible amount of curvature at the end, and we'll assume volume is very small, then you can, of course, take a covering, which maybe winds around these things a lot of times. So I'll just draw it like this, actually, right? So you're going down here. So you can take just a region here. In fact, we can take an open region if we like in Rn. In this case, it's in R2, which just winds around many times around this thing here and just maps down to this part in here. So I'm not looking at the caps at the moment. And you can do this, of course, just by winding around the cylinder. So this is an immersion. And so that if you pull back, here's you've got your initial manifold here. If you pull back the initial metric here, then you're just getting the standard metric, because this is just a flat cylinder the way I'm assuming this is a flat cylinder here with two extremely strongly curved caps. And then, of course, if you let the Ricci flow on this thing, then what's going to happen is, because we're choosing volume very small, this is going to shoot in very quickly and try and become spherical. So here you've got very, very small times. Depending on this volume here, you can make it as small as you like. So the curvature is, of course, as big as you like. It's way bigger than any n on t, whichever n you choose for small times. So if you pull that metric back up, then that's going to have the same situation. This is just locally in isometry. So although the curvature is getting extremely large here, and although this is completely flat here, we see that up here also that the curvature of the pulled back thing at this time here is also at some point bigger than or equal to n on t. So there's something going wrong here. I mean, we can't apply Perelman's. I get a nice solution to Ricci flow on this open region here, but I can't get the pseudo-locality, right? This doesn't happen. This thing is not going to be satisfied, although it's a nice region, completely flat. It's got a lot of volume. It's just a nice, you can put a ball of radius 1 in here. The curvature is getting as large as you like by making this volume smaller extremely quickly. So something's going wrong here. We can't just use Perelman up here. So I said we want to look at situations where we're, have solutions to Ricci flow that are not complete, or maybe, just defined on open things. So we've got to be a little bit careful. So one of these things here, we're going to have to actually somehow incorporate into any sort of local results we've got. In particular, something like at least some local sort of completeness condition will be necessary to get some sort of local results. Okay, we can't somehow get rid of this completely. That's not going to be possible, as this result shows here, this very illustrative result of what can go wrong with sort of local results here. Okay, so let's get on to the ideas now. What we want to do is actually try and localize some other results where I don't assume a Euclidean condition. So for example, here's a global result which doesn't assume a Euclidean condition. It says if you start off with something which has non-collapse volume everywhere, and scalar curvature bigger than or equal to -1, in the three-dimensional case, Ricci bigger than or equal to -1, and I am just at the moment restricting to this setup because I want to explain the global situation, then the Xi-Hamilton solution smooths out very quickly. Now we don't get any alpha on T. We've got some sort of constant coming in here which depends on the volume, and the scalar curvature is also not going down too quickly, and the Ricci curvature is not going down too quickly. So the picture that we generally draw in this situation is as follows. You can imagine you start off with something which is incredibly curved at the tip here. I'll just do a two-dimensional case. So you've got a lot of curvature there, but maybe this part's completely flat, so it's like a cone. So here, scalar curvature at time 0 is equal to 0. Here, scalar curvature at time 0 is incredibly large. And here, well, it's nicely controlled. Maybe it's like a sphere here. So here we've got scalar curvature under control, maybe less than or equal to 10 or something like that. And what this result says is that, well, you see, because this is almost like a cone, we've got this non-collapsing condition, so this volume condition here. Any ball you take of radius 1 is bigger than, the volume is bigger than or equal to V0. So this thing here is going to satisfy all these conditions. So if you do Ricci flow, so this is your M2G0. Now you do a Ricci flow, and you get a solution for a well-defined time interval just depending on this. The only thing it's going to depend on here is this V0. And the volume of balls of radius 1, which are all bounded from below by V0. And this thing here is getting smoothed out. So somehow, right, smoothing out, and you're getting sort of this Perelman behavior like this, but only for a short time, V0, but a well-defined time interval, and you're also getting bounds from below, which are showing you things aren't going in the negative curvature direction too badly either for the same region here. Right. So we see this result here. This is not, now we start to think about it and say, well, I can make an incredibly curved region here, and this is sort of a nicely highly curved region, and it's going to be smoothed out. So you start to think, well, maybe all these kind of local results work in the non-Euclidean case too, right? Even when things are not Euclidean. So I don't necessarily assume that my area, my volume of balls are almost Euclidean. You could have very highly curved regions. As long as they're non-collapsed, maybe you can get this control on curvature. And in this instance, as we see, you can. And also I managed to, some time ago, show this for Ricci curvature. So you see there's some sort of nice behavior going on. You start to think, well, maybe we can localize all of this, right? This is the idea. You want to localize this to this area independent, maybe, of what's happening out here. So we'd like to get rid of global information and just assume we've got some local information and hope that we can get a similar result to Perelman, that things get smoothed out in this local region here. And coming back to the question that was asked before, of course, this is only as long as your solution exists, and maybe whatever's going on out here could lead to a singularity or so on, but you want to still have control over the regions where you started off not too badly. Okay, so that's the idea. And, right, how are we going to do this? Well, maybe it's illustrative just to give a quick proof of the two-dimensional case in the global situation so that we can take some of the estimates that I get there to the local situation. So, yes. The non-collapsing condition is preserved up to a constant. Yeah, I didn't include that at this stage. I'll write it down later. Thanks for asking. So in fact, you also get volume of BGT of the same ball is bigger than, say, I'll just write V0 tilde, depending on B0, which is bigger than 0. Yes, for all t in this time interval, as long as the solution exists. Yes, right. Okay, and exactly these sorts of conditions we want to show for the for the local situation as well. So let me just, because in the global situation, a lot of the estimates and ideas that we need come up, and it's a little bit simpler to explain. So maybe it's a good place just to start with. So let's have a look at the global situation, as in the theorem I've got up here. Well, let's see. So we've got at time 0, we have some. Let's just say we've got the whole thing has got this, whatever the volume is, let's just assume it's bigger than some fixed constant, which we'll call V0. Okay, so it's got some volume. I'm assuming now M2 is compact. I'm just going to get some of the estimates going. And of course, we're assuming at time 0, this is the case. So the first thing is just quite simple. From the maximum principle, because this thing is the Ricci flow equation tells us that this is the case, and the well, this is of course with respect to the evolving metric here. Now I'm going to write this in a way, well, in the case that we're in 2 dimensions, you can of course take a general dimension here. Actually, let's just take a general dimension here. So you get 2 on, so I can just estimate this by r squared on n squared, for example, the right constant here, right? And then we know that this thing, okay, I'm going to use this later, but the first thing you see is that Rg of t from the maximum principle is bigger than or equal to -1. So this part's bigger than or equal to 0, so you get for later times that's preserved. Now in 2D, that's the reason I'm just giving this example here. We've got quite a simplification in that if you look at the evolution of the volume, this is all done by Hamilton, of course, then you get integral of the scalar curvature with respect to the evolving metric. And in the 2-dimensional case, we've got the nice information that that's just a topological constant. So it's just minus 2p times the Euler characteristic. Well, this is 2p times the Euler characteristic. So, well, we see that tells us then you can write down exactly what the volume is. So this is all well known. It's just a nice situation for this nice, just to get some estimates going. So we get, this is just plus 2 pi characteristic by t. And the first thing you notice is that you get some control on the volume. So volume mtgt, of course, if we're assuming this initial thing has volume bigger than or equal to v0, then you get that's bigger than or equal to v0. You can even take v0 on 2 as long as t is in some region here, which is, say, you can write it down exactly. It just depends on this Euler characteristic and the initial v0. So it's not collapsing too quickly as long as the solution's existing. Right, and now we're in a reasonably good setup, because what you can do is then, as soon as you've got non-collapse of volume and curvature bounded from below, you can just do a blow-up argument, and it will tell us that any solution of this type will satisfy that it's right. We need to do a little bit more. We need a distance estimate. We'll need that in a moment. So if we look at the distance of the length of any curve in the manifold, you just get that's equal to the length. I'm just going to write down the evolution equation for this thing here, Ricci gt, and then we're taking the directions of the curve and right divided by the length of this thing, which I'll just write like this, with respect to gt. So if we just normalize, then we see that this thing is nothing more than minus 2 by integral of the scalar curvature, because we're in 2D, up to a constant. And right, so then we see that that's, now what we're doing is using that the scalar curvature is bigger than or equal to 1, so we get nothing more than this inequality here. So that shows us then that the whole distance, if the length of any curve is evolving by this inequality here, then we see that the distance between any points, which is the infimum of length, has to be less than or equal to, say, 2d0 for all t. Once again, now we have to put in a new time here. If at time 0, the diameter of the whole thing is less than or equal to d0. Okay, so I just saw that the evolution tells us that the distance is not really increasing for short times. And once we've got that, we're in business, because now we can just use Bishop-Gromov Bishop-Gromov tells us now that the volume of any ball of radius t in any point is bigger than or equal to, now we take the volume of BGT of this big diameter, which we know covers the whole manifold now. I'm taking the volume with respect to the metric GT times by, and now we need some constant depending on d times r to the n. This is nothing more than Bishop-Gromov comparison. We just showed this is the whole manifold. This is the volume of m times by this c of d times r to the n. In this case, r to the n is 2. So now we've just seen that this is bigger than or equal to v0 on t for the times that we're interested in. So now we have to restrict. I did one restriction here, a restriction before. So we're going to have to take this time just to depend on the Euler characteristic d0 and x0, and this little v0 came in as well. Okay, so we're now down to always restricting these time intervals, and we get this nice fact that we've got non-collapsing. So the non-collapsing condition is sort of the crucial condition in just about all of these arguments. And I'll come back to way in the second talk. I'll just mention something about this non-collapsing way at the end. But the important thing is we've got the non-collapsing, okay? So once we do that, we now can just use a standard blow-up argument. We don't need to use any Perelman point-picking arguments here because we're on a compact manifold, so it's a little bit easier. You can just choose the maximum point of curvature, so to say. This case here now we can show is that all such initial manifolds where the volume is bigger than or equal to V0, any one of these, so a blow-up argument, implies then that the scalar curvature, we're just in 2 dimensions at this moment, is less than or equal to C0 on T for some C0 depending on all of these constants that we picked up along the way. But they're all just fixed constants, so I'm staying in some, if I stay in a topological class, I've got bounds on volume and D0, then we see that we're getting some bounds on the scalar curvature. What is the blow-up argument? Well, you assume this is not the case. There's no such, and also, of course, only for t small enough. In some new time interval now, you have to maybe restrict it. It's always, in all these things here, you're always restricting time intervals. And if you assume it's not the case, then you do a blow-up argument. You get constants going off to infinity. You rescale. You get an ancient solution. And this ancient solution has bounded curvature and non-negative asymptotic volume ratio. So you just now use the Perelman singularity result. And I'll just write it down here because we're going to use this later. Bound solutions, ancient solutions with bounded curvature and non-negative asymptotic volume ratio. That means, positive. Saying here positive. That means in the general situation that the volume of any ball of radius r on this at any time of this solution here, this ancient solution, is bigger than or equal to some, if I take Rn and I take the limit as r goes to infinity of this thing here, this is bigger than 0. Then, so that's just what that is. Okay, you have an ancient solution with BC, positive AVR, and non-negative curvature operator. Then we see that the thing has to be, the solution is trivial. So it's just isometric to Rn with the standard metric. at each time. And we see from our blow-up argument that, well, we've got everything satisfied here, except when we do our blow-up, we get scalar curvature equal to 1 at some point, so it's not trivial. So this would then tell us that, in fact, we have a contradiction. So we obtain then an estimate of this type. Right, so this is the kind of the simple setup, but the good thing is that I've explained here what we need later, this Perelman singularity theorem. I've also explained some of the estimates that we get here, in particular the one I got here, dt is less than or equal to that. In fact, let's just write this down in another form. We can write it down explicitly. What we get is that this is less than or equal to e to the 2t times d0 x0. Right, so we're seeing now that the distance is, at least in this direction, is not going too badly. Now we can finish this little section on 2 dimensions up by noticing that Hamilton also showed in this sort of setting where you've got bounded curvature of some type, he managed to get an estimate for the distance from below too. So let's just finish up 2-dimensional situation, the compact case, by mentioning this. So the 2D situation was that Hamilton, well, just generally, Hamilton, you can always estimate the distance between any points by the square root of the supremum of the curvature at that time. And now you see what's going on here. Is once we've got the supremum of the curvature like C on T, you see that this thing is like C0 on square root of T. And once you have that, you can integrate. Square root of T is integrable. So this is the nice idea of Hamilton, is that you don't just have supremum of curvature here, you actually get a square root of this thing here. So you could even have more, you could have C to some power of T, as we saw in Professor Tam's talk, and that would lead also to estimates on the distance. But in this case here, we just take the easy one here, and we just get, well, assuming I write this down correctly, dxy plus C0 square root of C0 times C of n times square root of t. So we get a little bit more. We don't just get that the distance is bounded from above, we also get that the distance is bounded from below. So we get this nice, there's a minus of course here. We get this distance up here with an E2t. Okay. So that leads us then to this nice distance inequality. So we don't just have control on the way the curvature is behaving in time and so on. We're getting some sort of infinitesimal information on how distance is changing, right? And at first it seems like, okay, this is sort of nice, but is that important, right? I mean, it's sort of, we're interested in the way the curvature is behaving and other things. But it turns out that understanding the way the distance is behaving at this infinitesimal level is very useful when it comes to proving other estimates, right? So this is what I'm going to be using in the next talk especially. But yeah, so now we've seen the sort of ingredients that we're going to need here. We saw the Perelman singularity theorem. Any ancient solution with non-negative curvature operator, positive asymptotic volume ratio. That's this thing here. This should be a bigger than, not bigger than or equal to 0, of course, right? Positive asymptotic volume ratio, non-negative curvature operator, bounded curvature is trivial. That's the one ingredient. We saw how we can do a sort of blow-up argument to get C0 on T behavior, assuming we have in control of the the volume quotients on the times we're looking at on the ball. So we needed this non-collapsing control. And the other condition that we saw is that we just use in a simple way the maximum principle to guarantee that in fact, yeah, here I wrote -2, but on the, this is because this is a different situation, but in the easy situation here we say it's not even getting bigger at all. And yeah, in fact, we can get this with a -1 here also in the general situation. For the local situation, we're not going to be able to get a -1 there. We have to always go down a little bit. So we've seen the main ingredients for how we're going to actually localize things, right? But it's also kind of illustrative to see how this argument's done without getting too concerned about the local information, right? So, and we came up with this very nice fact. We're learning how distance behaves here. We see distance is kind of going down and going up, but in a controlled sort of way, just depending on these constants, which depended on the initial volume. In this argument I gave here, it depended on the topology, and n, or n is 2 here, but generally we can do all of this here, this part here, as soon as you've got C0 and T control. Okay, right. So that's what I've just done. So now we want to localize these results. So this is going to be the part of the talk that I do in the second part of this talk, which is coming up after the next talk. So let me just say one thing before I stop. Well, in fact, these arguments about evolution of distance and Hamilton's result here, it's still up there. This all goes over to the local situation without any problem. Okay, so assume you've got some Ricci flow, and that for some x0 you've got some balls of a fixed radius. I've taken 5r, and they're compactly contained in M. So I said we're going to have some local completeness condition. And this is it in this instance here. I'm assuming at the moment everything is compactly contained in M. M itself is not necessarily complete or anything. It's just some solution to Ricci flow. Then all this part about the part I did on the distance, you can just take this over to this situation here. So, of course, in higher dimensions, you can't have scalar curvature bounded from below. You need Ricci curvature bounded from below. And then you get, for a well-controlled time interval, depending on the constants occurring here, the following information. So here it's just depending on K, and it's going to depend on R in a minute. Well, you see that you're getting this sort of control of the way balls are behaving. Your initial ball is remaining in a ball of time t with a slightly larger radius, and that's going to remain in your initial radius here for the same time here. If I restrict these times here so that SEKJ is less than 5r, that's all that I'm doing for this part here. And the other thing we're getting is then, well, not just that. I mean, that's a more kind of refined statement about controlling these distances, to just prove using the same estimates here. The other thing we get is this sort of e to the 2k behavior. So I said, in this case here, we've got Ricci being equal to minus k, so we get this sort of behavior. And what else have we got? So this part here just used Ricci bounded from below. Now if you take Riemann less than equal to some constant for your solutions, or more generally, you don't need to assume that the full Riemann curvature tensor, maybe just the Ricci is bounded by something C0 on T on these evolving balls, then what you get is, for a well-controlled time interval, you get also a sort of a different situation here now. The balls that you're looking at, you're reducing the radius a little bit, and then they're going to be contained in the initial one, but now you've got to reduce it in this way because of the estimates that we proved before. And then you see in the end what you've got is control of distance by constants which you've got absolutely total control over. So beta is a constant depending on n, k is the lower bound for the Ricci curvature, C0 is the condition, let's assume this one here. Then you're getting the same sort of control on the distance, and the proof of this is completely the same as the way I got the proof of these ones here. You just have to be careful that you stay in the region so that you can actually check the length of geodesics. So let me just make this one point. That's why we have to go in quite a bit to a ball of radius r instead of we started on a ball of 5r. Let me just make this one point before I stop. So the idea is remember, how did I get control over distance? What I did was I took 2 points, say x and y, and I looked at the length of curves between them that are in the region where we have the control. Now, of course, at a geodetic, we have to be a bit careful. Let's assume there is some geodesic between x and y here. Of course, it doesn't have to stay in this ball of radius r here if these x and y are far enough out. It might go out like this. And if it goes too far out, I don't necessarily have, because I want local things, I don't have Ricci less than or equal to C0 on t too far out. I've only got it on the ball of radius 5r. But that's why I restrict when proving the estimates to a ball of radius r, because that guarantees that this thing here is not going out, so I can just calculate the evolution of this length of this curve. It's staying in the region where you've got control. So this allows you then to really prove these estimates, and that explains why I actually have to go in a little bit and I assume that the conditions are satisfied on a ball of radius 5r. But apart from that, the argument's exactly the same as the one we did in the two-dimensional case. You just use the Ricci curvature lower bound that we had. So, thanks for your attention, and I'll explain the rest in the next talk. Which conditions are you talking about? Curvature bounded by C0 on t. Yeah. Oh, you're saying, yeah. So this is another question. So, I mean, first of all, I could take a global thing and that satisfy those conditions, so I could get something there. But you're asking, can we construct local solutions that, satisfy these things? Yeah, we can do that, but that's something that's coming in a new paper. So I'll talk a little bit about that at the end, in the next talk. Sure. Which one? Yeah, it went pretty quickly. This is the condition I'm assuming for all times for this statement here. Sorry? If I drop this assumption here, you're asking? Yeah. Oh, yeah. Oh, right. Good question. Thanks. Right. So no assumptions like that here. No bounded curvature assumption. Right. Just this. Assuming you've got Ricci, say, bigger than or equal to minus k, then we get the first statement. The next statement is that assuming this, then you do have some sense you've got bounded curvature, right? I mean, not at time 0 maybe, but, well, since it's a smooth solution, so you do have bounded curvature. This is only on the ball of radius 5r, so I don't, So what's outside, we don't know, right? And there's no assumptions on bounded curvature or completeness. The completeness condition is sort of lost now. What's happened is you're replacing the completeness condition by this fact here, right? That's. Good question, right? This can't be satisfied then, right? That must be wrong here. Yeah, it's a very good question. So I was going to say that right at the end, but yeah. So if you look at that thing. Now I'll explain it since you asked. It must mean that the ball, let's take it to say 5 or something, that what's happening is if you look below, it's coming in so quickly that the ball of radius 5 is, so to say, trying to want to come in above, so it's no longer completely contained. The ball of radius 5 above is no longer compactly contained in the region that you're looking at. Right? That can't be the case.
I can still review his talk in afternoon, the first talk in afternoon.